Yeah, I think already got Manu already asked me about stability thing anyway. So I think in this 45 minutes, next 45 minutes, I'll talk a little bit about the stability aspects of the DC microgrids for this common DC bus concept or common DC bus microgrid concept. Again, I think I'm not going to give a very deep or very thorough analysis of this study, because due to time limit. I think give you some, when you take away, you get some idea, how we can do the stability analysis for microgrids. Okay, what kind of concept we use? Because I think end of the day, the microgrids you're going to study will be different from what we are studying in non-university. But the methodology or the methods you are going to use, I think you can roughly keep the same, okay? And also the concept or the results, initial results, probably following quite similar. You're going to probably end up very similar conclusion when you study different systems. So I'm not going to go very deep of what the study we have done in non-university. I just give you some idea how we do the research, how we end up to here, and then maybe we can find some cooperation opportunities with different microgrids. And also, I think already Alessandro already had a good point already to look at the prediction of DC DC bus voltage and study from there. I think also quite interesting to look at. Okay. So this again is the system. So we actually we end up. So we'll have in the very beginning talk about this system. You got multi-generators. 2 generators driving by 2 engines, and APU driving another generator. And then you got motor. This motor, which is actuator for the aircraft, and this load bank. This can be used for the de-icing system. Heat up the wing, and also we might have, I think, DC chopper as well. Okay, but we simplify this system. We simplify this system to this 3 generators, and then the load is resistive load bank connected to another one. I think this here is the DC chopper. We'll have a DC chopper here as well. Of course, have a common DC bus capacitor connected to it. Okay, so what you want to do? Have this system. The first question you would ask yourself: so this kind of droop gain, what kind of impacts for this droop gain on your standalone system? Okay, for example, like the droop gain impacts on the stability side or dynamic side, for your system, can be either electrical drive, or electrical generation system, or DC-DC converter. That's the question you firstly have to ask yourself, and afterwards, we'll try to answer the question is, okay, we know the droop concept, the impact of droop concept on the standalone system. So what is we have multiple multiple generation systems connecting together, use the droop concept. What's the impact on the stability side for the whole system? I think there are 2 questions I want to guide all you guys through today. So firstly, we look at standalone concepts. Okay, what's the impact of this droop on the standalone system? We can look at the current loop. So for droop control, for droop concept, we said we have 2 different modes or different types. One is current mode droop, so which means I feed back the voltage to the droop block, and I give you the IDC reference. Okay, so this is called current loop, current mode droop. Okay, so as all these others are the same. Only thing is this is different. So you got VDC feedback to the droop block. Okay, so if you study the stability of a system, most likely will end up 2 ways. So one is use the state space. Okay, state space concept. You have x dot equal to ax plus bu. So this is a very standard one, and this started the eigenvalue of this matrix A. This one method. Another method, of course, using the the impedance. So we call that impedance analysis. Okay, this the method we're going to use. So but both way, doesn't matter which way you head into, you have end up to use small signal analysis. Okay, so we pretty go through the this concept, using the impedance analysis, based on the small signal analysis. So one of the to start with is, of course, you have this complicated control structure. What I'm going to end up with is a single line architecture. What's really happening is, firstly, the current loop here, because current loop is always, we say, when you design the current loop for the electric drives, you always have very fast dynamics in the current loop. So in that case, the whole current loop from IQ reference to IQ, okay, or ID reference to ID, we simplify as a low-pass filter, okay? So in that case, this current loop, so here, from ID IQ reference, okay, to the real IQ you get, I just simplified to be one low-pass filter, okay? This is IQ multiply VQ and plus VD ID multiply 1.5. This is the total active power, okay? This is, if you understand the machine well, you should understand this. But if you don't understand, essentially, from IQ, I can derive my active power. Active power divided by VDC is the current IDC, okay? So this is the whole lock will be about. So you go from IQ, I guess IDC. For IDC, you can feed back to the droop, okay? So this IDC either back to the IDC controller, okay? So this is the here. So you go IDC controller here, okay? So this is oops. Gosh, the mass. Here we go. So this is the IDC. Okay, we just show you the IDC control loop. So this is IDC feedback to here. So this all become the, if you can derive the IDC reference IDC. Okay, so this is called IDC control loop. Okay, and outside, of course, you have the IDC. You minus the load current, and in integration this current, you get voltage. Okay, so you got VDC output. So VDC feedback. So you got VO minus VDC. This is the droop 1 over K. Okay, so this is essentially the current mode droop closed loop diagram, single line diagram, and then from there, of course, you can use the small signal analysis. Okay, so transform this single block diagram to these small signals. So from the VO become delta V, and all this, this, yeah. So essentially, just do some mathematics. You can derive from this diagram to the small signal. So what's a small signal block diagram? Okay. So what's really interesting for us is, of course, firstly is the IDC control loop transfer function. Okay. Another one, of course, this this delta V to delta VDC. Okay. So let's look at the dynamics of this IDC control loop, okay, in the small signal analysis. Okay, very boring mathematics, so I'm not going to show how we derive it. Essentially, you can, if you spend some time, you can end up with this equation anyway. What's really interesting is this one. So for the current loop, current mode droop, okay, you use the droop concept. What you really end up with in this IDC closed loop, the IDC control dynamics, you have, because it's minus, you have a positive 0. So you have a 0 on your on the right plane. Okay, so this positive 0 will give you a lot of challenge when you design the current control loop. Okay, this is something you should be aware of. So when you do the, when you go back to do your mask grades analysis, you should be very careful when you design this inner loop, the IDC control loop. You find out, well, you might end up with different conclusion because for here we use the electrical drives. For you, maybe use the PV panel, maybe different. But this is something you should be aware of. So the methods we're using, as I said, is small signal analysis, and the way you derive this, of course, always start from this kind of single line diagram. Okay, start from here, and you can derive the transfer function essentially. Okay, so the VDC control dynamics. So essentially, delta VDC over delta O. So the change of the DC link voltage essentially, find out whatever. So this is this kind of form, but it doesn't matter. Don't worry about this. Essentially just substitute here to here. So what's really interesting is you look at the K here. So what's really found out is the K is actually in this the VDC dynamics. So essentially what's really happening, what really tells us is this droop gain will have impact on the dynamics of the system for the current loop, current mode droop. Okay, so this is something you should carry away with when you do the your droop controller design. You might end up different transfer function, but I think that's something you should look at. So you look at if the droop gain has impact on the dynamics of the system. For the current mode droop, yes. So another one is the voltage mode droop. So essentially, what's the difference? Everything is the same apart from you have the current feedback from the local or common local DC bus to the droop characteristic droop controller. Okay, and output is the voltage reference. Okay, again, we do the control block diagram. Okay, here, so we really have this is again. So you see IQ reference to IQ again. It's like a filter. Okay, and then from the BDC here you have a control block. Okay, to give you IQ reference. This reflecting. Oops. This reflecting. Anyway, so this, and then here we go. So from IQ again, it goes this kind of power, this kind of power calculation, and then from IQ you go to IDC, the relationship. Okay, as we discussed, like the same as the last one. What we really have here is, of course, you got voltage feedback to here, and then this is the VGS controller, give it the IQ reference. Okay. And then the droop itself, you see the droop itself is from the current I/O at the feed forward K to the to this loop to the current point here. We find out actually, if you very familiar with control theory, this is more like feed forward control, and this should have no impact on the dynamics of the system. Again, we do the similar transform. You find out this, you do small signal analysis. And you find out, similarly here. Okay, so exactly what we did for the current mode droop. Okay, again you see that this K here. So this is the droop. Okay, so the K is like feed forward. Okay, if you look at the equations here, the dynamics related to VO. Actually, you have no K, okay, you have no droop gain in this equation, so there's no impact from the droop gain at all. Okay, so which means the voltage mode droop actually don't really have impact on the dynamics of the system. Okay, this is something very interesting to say, and the reason, as I said, is really because this is feed forward, simple as that. Okay, even you don't want to derive. Don't derive this equation like this. The concept is quite simple. Okay, so this is the first question. So the impact of the droop, okay, on the standalone system. And everybody knows, this constant power load is always a big problem for the electrical system. So in electric aircraft, or in general, there are two main types of constant power loads. One is the DC converter. So essentially, what's really happening is DC converter control the voltage here well. So in that case, if you resist load, the power here is constant, which means the power here is constant. Okay. So this is why we call this constant power load, because the power is always at this point is constant to the load. Okay. So another one is the AC drive. So what's really happening is for the AC drive, you produce torque and then spinning the load, whatever. So if the load and speeds are constant in the load side, what's really happening is on the DC power side, you attract active power, keep constant. Okay. So what's really happening is the mechanical power, essentially the active power. Okay, so in that case, if the machine draw such amount of active power, which means this DC bus I should supply such amount of power. Okay, so if the load is constant, the speed is constant, of course this will be a kind of constant power load. So these are two main constant power loads. In general, what's really happening is if you look at the impedance of these two loads, we find out these two impedance, these two system impedance is negative, which is what we call the negative impedance impact, which essentially have a huge impact on the stability of the system. Okay, this I think is something you should be very much aware of as an electrical engineer. These kind of constant power loads always have bad impact on the system stability. Okay. And the way to study, like I said, the stability issue is the impedance. Okay, so one of the methods using the impedance. So here we define the this simplified system. So essentially, you got source converter and you got load converter. Okay, so source converter, of course, from the machine to generator and supply the DC bus, and then the load converter is from DC bus to the converter and then supply. Either the DC converter or DC converter, and then afterwards is a DC, whatever. So essentially, what's really happening is the voltage here on the load side is essentially like the resistive parallel series circuits. Essentially, have this the source, output source, and the impedance of the output impedance of the source and the input impedance of the load, essentially, and then you have this kind of these two impedance connected in series, and you calculate the voltage, essentially. This is very much like the resistive circuits in series. Okay, we will learn the first year. I think the first year students can do this if you give them the concepts. Okay. So source converter is the controls bus voltage, and then the load converter is the control the load current. Okay, control the current and power. It's the key thing you should be aware of. Okay, so this is the so essentially for different modes, voltage modes, the current modes or the current modes the two types. As I said, one is the local voltage feedback, another one is global voltage feedback. There's three types of droop control. What's really happening is so this side, you have different for the multi-modes, you have exactly from what we studied before anyway. You got this voltage, control voltage, and then you got our circuit. And what's really happening for the source impedance, you look from this side, and the load impedance, you look from that side. I'm not going into detail of this. I think if you go to read a paper from Figao, our students, you probably see more detail. Essentially, what I want to tell you is again, it's based on the small signal analysis, and then we derive this equivalent circuit. Okay, to look at the impedance of different droop control modes. Okay, so the voltage mode, you see, we represent as the voltage source, and the current mode we use we represent as a current source actually for the modes. So, what I want to say is now we look at the source impedance. Okay, so we look at source impedance on this side, from the voltage modes, from current modes, LVF, and then the current mode from the global voltage feedback. We look at what's really the source impedance would look like. Okay, in this, and in this, well, this is a very complicated, scary equation here. But what's really want you guys to carry it away with is you look at the Bose diagram. Okay, so this is the impedance, source impedance from the two current modes droop control. Okay, so this answers Manuel's question. So essentially, if you look at the droop control, so current modes droop control using local voltage feedback, or use the current mode control using global voltage feedback, you find the Bose diagram. Very similar. Okay, so what's really happening is it says indicate that the stability characteristic of this LVF local voltage feedback and the global voltage feedback are very similar, essentially. Okay, because the Bose diagram, they're very similar. Well, essentially overlap each other. So in that case, it seems that no, for stability-wise, there is no difference between global voltage feedback and the local voltage feedback. Okay, so in that case, for stability studies, in the following, I just refer the local voltage feedback using represent the current modes in the following slides. Okay, so. So now, if we know we know this small signal analysis we present for each mode. Okay, we just essentially we have these different systems, different sources connecting together. Okay, what's really happening? You just transform all this using the small signal analysis circuits, essentially representative circuits, and connecting parallel, and then do the circuit analysis and derive the impedance of the source. Okay, so you have multiple sources connected together. I want to look at what's the source impedance look like. You can either do it this way, or the very complicated mathematics. Something you can do is you use the VOC open circuit. So you have open circuit here, you derive the VOC here, and afterwards you do the short circuit test. You go short circuit this here and look at the short circuit of this current at this stage. Okay, so essentially you use the open circuits over the I short circuits. You can derive this CS. Okay, essentially this again is the methodology I want you guys to use as well. So because for you guys, you might look into different systems. For you guys, the method is the impedance of the source can be used, can be calculated in this way. For us, more interesting when the system connecting parallel, what's really the source impedance look like? Okay. Before I move on, I think I'll talk a little bit about this kind of concept of global droop gain. This kind of concept. Okay. So essentially, the global droop gain essentially talk about the droop characteristic of the DC bus and the DC current. Okay, so instead of local current and local voltage, DC voltage, we're looking at the voltage and current relationship in the bus, in DC bus. Okay. So for the current modes, as I said, current modes RVF, the local voltage feedback and voltage mode system. The bus voltage essentially, is equal to VO minus the droop gain K1 plus R1. You certainly you can calculate it using the droop concept essentially, and what you end up with is the global droop gain. So essentially, the bus voltage and bus current is in this kind of form. Okay, essentially, you find out all the droop gain just 1 over everything adding together. Okay, this is one the global droop gain for the local voltage feedback current mode and voltage mode systems. Again, the same for the global droop gain for the current mode global voltage feedback is this global droop gain looks like this. What's really happening is you find out this global droop gain doesn't matter is current mode or voltage mode compared with the each individual droop gain is always stiff. Well, stiffness always increased. So this is the individual one. This is the total or the global droop gain is always stiff. The stiffness is always increased. Okay, so this is something very interesting to look at. We can come at this point later. Essentially, with this increase, essentially will increase the stability of the system. Essentially. And this will be reflected actually in the next few slides. Okay. So this is some results actually. Essentially, so the we do the simulation study actually at that time. Just you see in the system, this is only one generation system. So only one converter is working, one generator is working. So you have keep increasing the load, the power of the load, and at this point I connect the second generation system. What you find out is the voltage, discharge voltage increased, okay, and the current actually reduced. So what you find out actually what essentially tells us is the droop gain, the global droop gain starts working. In that case, the stiffness increased, okay, when this generator 2 system connects to the grid, okay. Of course, when you do the analysis, of course, another one you have to look at the impedance for the loads as well. I'm not going into detail of this, but I think mainly focus on source side because the load impedance, either constant power load or resistive load bank, is widely studied in other literatures. So I'm not going to very detail of this thing. What you find interesting, if you have this multiple sources connecting this in parallel, you look at this is the load, the impedance of load ZL. So I just give you the board diagram of this load impedance, as it is. What you find out is when I have multiple generation systems connecting parallel, which I use the current mode control. So again, as I said, current mode control. Here I just refer to the local voltage feedback, but the same as global voltage feedback because the impedance wise, the source impedance are the same. Okay, so you look at the source impedance when I have multiple sources connected together. So with this n equal to 1, and then when I increase, we find out in this area they are shifted, inwards. But really, don't really have a big difference here. So when the frequency is very low, okay, you might see a little bit difference here. Okay, it's beneficial to the stability, but not that much this way. And also, you see this negative impedance here. So this black line is the load impedance. You find out the phase angle is 180 degrees, which means it is constant power load, which means it goes negative impedance because the phase angle is 180 degrees. Okay, so essentially what's happening, so is you have some gain, in the stability range, okay, but not too much. If you go to the so this is a fixed global. So here I forgot to mention we fixed the global gain, okay, KT to be constant. Another way is I fixed the individual droop gain. So for the separated system, the droop gain is fixed. The Ki is fixed. Okay, the local droop gain is fixed. So what's find interesting? You connect this in parallel. If you see the difference between the two systems, what we really find out is when you connect from z to 1 to 3, what we really find out is actually, it's getting away further from the load impedance. In that case, I increased my stability margin essentially. And again here, the load again is the constant power load, which means the negative impedance. Okay, as I showed here. If you want to see more clearly, so this is the Nyquist diagram. So essentially, some conditions. So assume the droop gain, local droop gain is Ki is fixed. So what we really find out is this. If there is this is the pole here, so find out it's start to shrink. The Nyquist diagram it starts to shrink towards that direction. So in that case, they increase the safety margin or the stability margin of the system. Okay, so this is very clear to say when the numbers of multiple source increased, actually it's getting more and more stable of the system in general. Okay, so again, so afterwards I think very briefly, afterwards we again set up this kind of test rig. You have multiple sources. Again, but for this particular case, we use the grid, okay, not the AGAR system. So we build another test rig to test all this theory, part of theory we developed so far using this test rig, and this is the rig we tested. Very complicated. So Feigao, our students have done really good work in 3 years PhD. 3 years PhD. So essentially, from nothing to this. Okay. So you have, he finished his PhD, and now afterwards we essentially destroy everything, and now we put it back in a more nice way. Essentially, you have 3 converters. I think, do I have any figures afterwards? Yeah. So we have 3 converters. Semicube, we have this is AC conductor, so connect to the grid, and the resistor is a load bank. And then what do I have? Yeah, the transformers. Transformer is not, you cannot see here. So essentially, what's really happening? You have you have converters. You have 3 transformers. You got 3 converters, and you got the load bank and the DC chopper. Okay. And what's really happening? This chopper is here, and this converter is here, and then this AC inductor is somewhere between the we essentially try to put between the converter to the DC bus essentially. Okay, and this is the breakdown. Well, brief breakdown of the hardware thing. So this is the, I think if some of you have been to Nottingham, you should be aware of this. So this is what we developed in Nottingham University. So the DSP we use Texas instrument anyway. 6813, I think, was what we're using. The daughter card, and this FPGA is developed by University of Nottingham. And this is the sensor board. Oh, sorry, sensor board. I mean interface board. So connecting the sensors to the DSP FPGA boards. And this is the Semicube, and this is a commercialized product essentially, 20 kilowatts each, and it got 3 of them. Essentially, this is a 2-level converter. Okay. So the experiment results. Again, so this was the current mode testing, fixed Ki. So what's really happening is we have 1 converter in the beginning, okay, and afterwards we connect to convert together. So you find that this mainly, to show you that the this to essentially improve the stability, because you see the I think I didn't show the previous one. Sorry. I think this is not the final version I prepared. If we have only 1 converter, the system will not be stable when it's 6 kilowatts. But for this current mode testing with fixed Ki, what you can do, you can increase to 7 kilowatts with no problem at all. Okay, so this is something strange. Okay, anyway, never mind. I should have more slides actually. We show the experiment results, because I should have show you the single. When you use single system, we have only one converter working. Only one converter working is actually this system is 6 kilowatts is not stable anymore. But we have multiple sources connect together. If with fixed Ki, we are increasing the shift margin because even 7 kilowatts is still very stable for this system, essentially. And actually, up to the end, yeah. I should have more slides, but yeah. Anyway, it's a quick summary. Essentially, I think it's a pretty good idea. Anyway, so for stability analysis, we study essentially. We do droop control. The first question is, what's the impact of this droop gain to this standalone system? And secondly is, what's the impact of if we connect all these systems in parallel to the common DC bus? And then what method we're going to use? So we're going to use the small signal analysis, okay, and based on impedance. The message is, firstly, is the global voltage feedback doesn't really give you benefits in terms of stability, okay. But paralleling multiple sources will have, would be beneficial for, for the system stability study, actually, for the system stabilities. And also we develop all this theory, well, some of the theory actually, because we require a thorough study of this stability for this system. And we also set up a rig in Northern University, and then we validate our theory using the experiment. Okay, so I think I will stop here for you, and then if you've got any questions, you can ask me in a tea break time, I think. Yeah, because I think it's tea break, 10:30. Okay.